Okay. So, good afternoon, everyone. Am I audible to all of you? Good, good. So, all right. I saw that some of you have attempted the questions, and I'm happy to see that some of you have done pretty well. I'll be giving the marks on the questions very soon. All right. So, let me just turn off my phone. Good, 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 good. So, let me. All right. Today, although it's a session number 4, but since we have only finished till session number 2, we'll be covering the session number 3 today. All right. This is a fourth session, although. So we're lagging behind by one session, but that's all right. Okay. That's all right. Good. So, so do you have any questions before we move forward? All right. So let me. Okay. So today we are going to first demonstrate to you how do you use a streaming job, or should we discuss the last session's question first? Yes. Okay. Okay. So let me demonstrate to you how do you use a streaming job first, because a streaming job is easier, and using a streaming job you don't have to code too much to get your mapper and reducer in place. All right. So let me take an example. So the way you generally run a mapper reducer is in this form. All right. So first of all, let me explain to you what is a streaming job. A streaming job essentially a library which makes it possible to use any binary as mapper or as reducer. All right. No matter what kind of binary is it, it makes it possible to run it as mapper or reducer. As long as the mapper is producing key and value which are separated by a tab, it is completely okay with the streaming job. All right. So this is the example. Let me take it out and show it to you. Is the font visible enough? So first line says that Hadoop is the command line, which is the client. And when we say jar, it is going to execute whatever bundle, whatever library you give in. In case of a Java, the library is in this form. Okay, so Hadoop streaming is a library which itself is written in Java, but this library makes it possible for you to write mapper and reducer using any command. Okay, so this is the command which launches the Hadoop streaming, and it takes the first in argument as the input folder. So this is our first argument. Okay, This is our second argument, which is output folder, and this is our mapper command. Okay, mapper command. When we specify mapper, we can always say something of this sort. It essentially says that execute mapper is a command called sed. Sed is stream editing. It has nothing to do with streaming job, but sed is an editor, command line editor from Unix, which basically replaces one string with another. So whatever input sed would get, it will break the spaces into new line. Okay, or it will replace the space with new line. Sounds good to you? And and the reducer is of this form. Okay, so basically when it breaks each word into one line, meaning every space becomes the new line, so you will be left with one word per line, and that one word will automatically become the key, because and the value will be null. Okay, value will be blank, because we just need to count the values. Okay, let me show it to you. All right, so is my screen visible to you? Not Hadoop, not root. We want to go into student. So all of you are now able to access Ambari and Hue and command line, right? I saw an email where you were able to access Hadoop. You were able to access Ambari. And are you able to SSH, all of you? Because I saw email. Okay, so Ambari is not working because of IE issues, Internet Explorer issues, or is it working in Firefox and other places? So you are using Internet Explorer to access Ambari? Okay, okay. Because the message which I got saying you could patch this Ambari is actually for the non-standard browsers. Okay, so for Google Chrome, it should be different issue. Okay, okay. So, so Chaitra, could you, after the session, could you give me a GoToMeeting control and I have a look at it? Okay, right. Let me have a look at it, because yesterday nothing was on Saturday, Friday nothing was working. So, all right. So good, good. And yeah, all right. So, moreover, Ambari is not that much required. What we require is Hue, Hadoop one. This is what we require more, and what we need more. I mean, the most important is SSH, and then is this web interface, and then is the Ambari access. Okay, SSH, Hue, and Ambari. That's the order. Good. Now we can run our command like this. Okay, what we said is Hadoop jar and our library name, and then we gave an input folder, and then we gave a output folder. Now since it is in new line, we'll have to bring it in the same line, and then it will run. It says that the output folder already exists. So let's just change the output folder name. Let's call it output and ITC. And I will call it, instead of my login, I'll call it as Giri. So basically what I'm saying is take the input from this folder as Giri word count input. If you remember, we had big.txt in this folder, and we'll be putting the output into as Giri and output ITC. Okay, so starting, and whenever it starts a process, it gives you a URL to track the status of your job. And in case you want to debug what exactly happened, all the print statement, everything, you can be seen here. Okay, so you can see that it is being executed on node number 4, Hadoop 4, and logs are here, right? So you can see the logs here. All right, so it's taking some time, it's throwing some errors. Command failed, it says failed map tasks are these many. And let me have a look, why did it fail? Container, let it load. Okay, so it says that this is waiting for replication, deleting. All right, let me see if all nodes are fine. Okay, so secondary node is down while my, okay, this is okay. And what about MapReduce? This okay. Yarn is giving one error. Oh, one of the nodes are down actually. Disk is free while memory is close to full. And what does it say now? So all three node managers are live. Let me give it a third attempt. So basically one of the node is down. But in case of this node being down, the load should have been shifted to another one. Node should have been shifted to another one. Let me just copy the URL of MapReduce. So it says map is 0% and reduce is 0%. Let's see what happens. I'm scrolling up. Hmm. So this is our job, and out of two maps, one has succeeded. So first attempt failed, second attempt worked, and we can look at this. So anything you write on, if you are writing your own program, and in case you're writing onto std out, you can see the logs under the task, under the attempt. Okay. So on the top level, there is something called map reduce. So under each of these sections, if you click on to running all of this, you can go to logs, and here in the logs, not this one, it's loading, show you all the things which what's going on. Okay, so this time it has worked fine. All right, so in between you can also see that one of the node has failed here after 50% of map was completed. Then and first one attempt failed, and then there was second attempt, and then it worked. Now it has completed it successfully. And all these statistics are very important. Okay, these statistics, do you see here, number of byte reads, okay, and failed map. I mean, the more important part is this, the map reduce frameworks performance. Okay, so if the time taken, if the time taken, or at least this portion, you can have a, you should take a note of it. Specifically, if you are doing a performance, then you should basically look at these numbers, and we will discuss about this part. Okay, so we have created output ITC 3, and under this, so it has created this output folder. You can also check on the web browser here and go to the file browser. So right now there is only a single reducer, so we have got only one part, and it has produced this output. All right. So we can say hdfs minus hdf Hadoop fs tail, and this file will show you the last few lines. Right. I think 20 lines. So it has shown you the count of each word. All right. So basically, using this command, we have generated the word count. Using the streaming job, we have generated the word count. So look at this way. What exactly happened when we did streaming job is this. So we had some text file, text input file, which has lines, and each line had words. After we replaced space with a new line, it became this. Right? Now, when it became this, each word, each first word of the line is considered automatically as key, and the next word after the tab is considered as value. Okay? The first word before the tab is considered as key, and rest is after the tab considered as value. And here there is no value at all. All reduce did was all reduce. No. So Hadoop essentially here, when it was doing the streaming job, all it did was it just sorted the data and gave it to your command. It did not do the grouping here. It did not do the grouping here. All it did was took your data, sorted it, and gave to your reducer. Here our reducer command was unique minus c, and unique minus c essentially, given a sorted data, it computes the unique counts. That's all. Okay. Ideally it will be the other way. Okay, it will be like this. Unique generates the number like this. All right. So basically, we used all. I wanted to demonstrate here that we did not have to write a single line of code. We never had, it did not have to compile anything. We just used our standard Unix commands to do the word count. All right. So in more details, if you increase the reducers, this is what will happen. Some of the keys will go to the first reducer, second, keys will go to the second, and some will go to the third one, and they will be storing in different files. So effectively, this is sort of an output. All right. So you can, this is for multiple reducer. Okay. So this is for streaming job for more reducers, more than one reducer. All right. So streaming job looks okay to you, or did I skip a lot of things? So streaming job essentially first runs your mapper on all the records line by line, and whatever is returned by your mapper is sorted and split it into multiple reducers. And on each node, here one thing you should note is before giving it to the reducer, the data is not being grouped. It is just sorted and given to each of the commands. Is streaming data different from text? It's a standard text input format actually. Okay. But there also you can in a streaming job also the default input for the streaming job is actually text input format. In case you want to change that, you can change that. All right. All right. So using just a simple command without any code, we were able to do word count. We were able to do the word count, and this will come very handy for you whenever you have to do a quick churning. If you are good at Unix, if you know a couple of commands, this will come very handy to you. All right. Now, question comes in: what if I have more than one command in my mapper, or what if I have more than one commands in my reducer? What will I do then? Okay, here is just one command which I put on the command line itself. What if I have like 10 commands? If my script is complex, what am I going to do? Right. Also note that SED is a standard binary available on the Unix. What if my binary which I want to run on as a streaming job is not available on all the nodes? What would I do then? In those cases, so to solve that problem, I'll do two things. First, if I have multiple commands, a complex command with a lot of pipe separated data, pipe separated commands, this is what I'm going to do. Put that command inside a script. Say here I'm saying mycmd.sh. So just now what I demonstrated to you, the data was not cleaned. Okay, the words were just separated by space. What if there were multiple spaces between the words? What if the word had punctuation marks? What if the words were in the lowercase uppercase? So to clean that up, I have written another script, this one. What this script does is, first it replaces space by new lines. Okay, it replaces space by new lines, and after that what it does is it replaces a small anything which is not alphanumeric with nothing. So this basically syntax says that anything which is not A to Z, capital A to Z, or 0 to 9, delete it, replace it with nothing. Okay, basically delete it. All right, so here there is not a space, it just delete. And then I have said translate from caps to lower caps. All right, so these are three commands which are chained together, or which are chained by a pipe, which are basically the output of first SED will go to second SED, the output of second SED will go to TR. Okay, so first I changed the space with new line, then I removed all the non alphanumeric characters, and then I translated upper caps to lower caps in a single command. Okay, now what I did was I wrote this command in a separate file. Okay, and I call it mycmd.sh. Okay, so you can see I've already done that. Now the next thing I did was so once I have put that in a separate file, what I can do is I take it and execute it. Now reducer remains the same for time being. If you want to do further churning in the reducer, you can do. For example, in the reducer, instead of instead of printing the counts before, you can print the count after by using cut or by using awk. You can do that. All right, now notice the last argument in this, it says minus file. So this file is going to be shipped onto all the nodes. If you mention anything in the file, whatever command you have, it is going to be copied to all the nodes before getting executed. Sounds good? So let me show you this one here. So output will go to, let's call it ITC. Right, so it's starting your word count job, in which we are cleaning up our input really nicely. We are removing all the special characters, we are only leaving lowercase alphanumeric words. We'll remove all punctuation marks and everything, and will generate more meaningful results. Okay, so yeah, looks like some of the nodes are not in good shape. I have to review this, but that should not stop us from getting output. Attempts are failing. Number of attempts. I produce two total, one running, yeah, two running, one pending out of total, and both the one which is running has got one task, and the task has got so many attempts. So it failed thrice, it is trying fourth time, and every time it says that there is an error. Let's have a look at the logs. So you click on the logs. So it says that cannot cannot allocate memory, and this is happening on which node? This is happening on Hadoop 4. Hadoop 4 is full. Hadoop 4 is not giving results. Then it tried Hadoop 3. Again, Hadoop 3 is also saying the same thing. Now, what does the third attempt in Hadoop? Says again cannot locate the memory. And this one, what does it say? Okay, so out of two, one is complete. Okay, first task failed. Task. Okay, this one succeeded. Hadoop 3 is working fine. Right. So basically, 5 failed, 1 successful, reduces 0 failed, 1 killed. Hmm. So basically, alright. So it says the URL to track the job is this. Hmm, cool. So this one has worked now. Alright. So let me see. It's word count, output ITC. I think first one command has been successful. Alright. So I go into asgiri folder and we have word count output, word count, word count, output ITC1. Yeah. So this has been successful. Okay. So this has been successful. Fine. So previous task was successful. It just I did not see that. Okay. So basically, if you can see now, the data is quite well cleaned up. It doesn't have those special character. And if you go to the last block, you will see, can see that now. And if you want to have a look at exactly what does it look like, so what you can see is Hadoop fs minus cat, and then what you can do is sort minus INR. All right. And this sort minus NR, actually you could move that also to next set of MapReduce. So it's quite clear to, if you see. Now you can see the word called the has come maximum number of times, while space is come less number. I mean less than that, and then off and to this that and so on, right? So if you remove the normal prepositions and normal words, you will know that what is it about, what is this book about. So most likely you will figure out the whole book is about the protagonist is most likely this one because that's the first word, and he is a prince. Okay, so it the whole book might be based on Prince Pyre, right? So if you do the words analysis on a big book, you can easily figure out that what is this book about. Okay. Okay. So Sasikant's question is, what does this signify? Map 50%. Map 50% as in 50% of the total data has generated the key value pairs, right? Because 50% of the total blocks or 50% of the record inside each input is split have been processed. All right. So sounds good, sounds relevant to you. Okay. Let me make a note of few things. First is I need to check nodes. Some of nodes are failing. Okay. All right. So, but that doesn't stop us from trying out because Hadoop will delegate the work to other nodes and we'll get it done. Okay. So sounds good to you? No? So basically, I was trying to demonstrate to you if you have multiple steps to do in input, then you can use a full-blown shell script. The input std in to this script is the input from the file which you are giving to the Hadoop command. Okay. If you are specifying here a directory, if you noticed, we are specifying a directory here, right? When we specify directory, all the files inside this directory will be concatenated and given to the mapper and the reducer. All right. So good. So hands-on is done. Now, one more thing. If I had to write the same command, what I'm doing here. So I have got say mapper this, and let me take it out, right? So basically these were the arguments. If I have to replace this with a single Unix command, all I will do is cat star, and then whatever is there you pass it to the this command. Okay, right? So whatever cat this directory, pipe all of the content. Cat basically reads all the data from a file or list of files and send it to std out. Std out becomes the std in because the data is going from left to right to SCD, and SCD basically takes the data, replaces spaces with new line, and then all you do is sort. Okay, so this sort command is what is done by Hadoop for you, and rest of the things are as is. Then you pass it to your this command. All right. Okay. So if I had to replace the same thing, same command with a single command line, this is what I'll do. Cat whatever input files I did, okay, then run the mapper. Sort is the thing which Hadoop is doing for you, and then you do a reduce. So basically what I'm trying to demonstrate to you is that this command you see here is equivalent to this one, just that this command, this command is being run on one machine and this one is being run on multiple machines, right? Not good. So if you have to test your streaming job, test your streaming job, this is the syntax you could use. This is the syntax you could use. Okay, take your mapper command, take your reducer command, pipe them using sort, and then you save the output to the output folder. So this will quickly give you the results exactly similar to what Hadoop is giving. All right. So any questions? So was I able to explain or did I skip too many things? Okay, for Kumar it's fine. For Tuntan. Yes. Any questions still here? Good. So should I assume that we are all good and move ahead? I'm waiting for your questions. Yes. Please feel free to ask. If you did not get it, I can explain again. And all right. All right. So, okay, one quick question to all of you. All right, Prasant's question is performance, which one is better, Unix script or MapReduce? So, the difference in the performance will be only smaller and will be equal to the time taken to launch a program. So, for Hadoop, launching a Java program is far more quicker than launching an external script, right? So that's the only latency difference you will see. So you might notice a difference of maybe half a second, okay, or maybe half a second into nodes multiplied. Say if you have 10 nodes, so it might go up to 5 seconds difference. Which one is better, Unix script or MapReduce? Yeah. So performance wise, they are almost same because here when we talk about Hadoop scripts, the scripts actually run for hours or run for 10 minutes, 15 minutes and so on. So yeah, a few seconds, Java program might be few seconds faster. Every problem can be solved by script. Theoretically, yes, but sometimes it becomes quite difficult to get something done using shell script easily. Say for example, you have to pick up third character from every word. Okay, if you just have to make the key as third character of every word or summation of ASCII value of each characters, so this kind of operations is quite difficult, right? But if you have a binary for that, if you have a legacy binary, you can actually use while using Hadoop stream, you can use a legacy binary. How do we configure the multiple reducers use in streaming? Okay, that's a very valid question. So, so there is an argument. There is an argument called. Okay, where is this slide? All right. So there is an argument of Hadoop streaming. Okay, Hadoop streaming here. So specifying number of reducers, you can specify minus d mapread as 2, 2 or whatever you want to use. Okay. Okay. So you can see the documentation available here. Okay. So there you can see that MapReduce task is MapRed dot. There's an argument which you can pass by this. All right. Now here, let me just put it. All right. Good. Now let me get back to the question. So do you have any other question with respect to streaming? Streaming is a handy way of using your commands as map reducer, mappers and reducer instead of writing the Java code again and again. I will show you the Java code. Ideally, if I had shown you the Java code first, you would have really appreciated the streaming job because Java code requires a lot of typing. All right. So problem discussion. Does anybody had a problem with this one? So do you need mapper reducer for this kind of question, or doing it on a single node is good enough? Anybody? Depends on data size. Very good point. For big data, MapReduce is needed. Why? Okay. Nasruddin and Prasant. I agreed, completely agreed, that for big data, MapReduce might be required. But why do you think so? What is it that becomes the scarce? What is it that becomes the bottleneck? So Satyanarayan's point is that if data is more, CPU consumption is more. Do you guys agree? Do you think it is the CPU that is going to become bottleneck? Because here we just have to retain 26 variables in the memory, and we just keep on reading the data and update these variables. So do you think the CPU will become the bottleneck, RAM will become the bottleneck, disk read write will become the bottleneck, or network traffic will become the perfect, perfect. So the block here the network reads as well as disk read write will become the bottleneck. Very good point. Great. So everybody agrees that if the data goes beyond a certain size, such that the network and disk reading will become the bottleneck. Then you would require the MapReduce. Otherwise, using it on a single computer is good enough. And if I ask, what is the complexity of this algorithm? Those who are from computing background, they can tell me. So, how the time taken by this algorithm on a single node will vary with respect to the data. If data grows to twice, the computation will become twice or more than twice. Slightly more than twice, because of the disk read as well as CPU. Both consumption will increase. But theoretically, the complexity of algorithm is O(n) on a single machine, because for if there are n number of characters, we just have to do n number of updations in an array, right? And mostly this array lookup is extremely fast. So the CPU will not be the bottleneck, it will be the disk read and network. Good. Great answers. Moving on. All right, so here we have. So without MR, you just create an integer array of 26 size, scan the text character, and increase A0 for small a, and increase A25 for Z, and others in between, right? Now, at the end of day, you will have just 26 numbers. Now, without MapReduce, without MapReduce, this is what you're going to get. Sorry, this was without MapReduce. Okay. The problem is with mapper and reducer. If you notice, the mapper will produce a lot of keys on a single machine, which are going to just get sorted on each machine. And it's not 26 numbers only, or it's not only 26 numbers which will get transferred to the reducer. It will be more than 26 numbers, because you will be generating like this, right? So on each mapper you are going to have a on each mapper. This is a result of, like, on each mapper you are going to have this. Okay, you are going to have, and so on. So 23 times, 234 times, or so on. And similarly, B also, these are going to be A1, B1. Here the example is with respect to a different case, right? So here the result of each mapper, or all the mappers, is going to be something of this, say, 1000 times. Okay, and B 10,000 times, or maybe a big number, howsoever characters are, right? That is going to be the output of each mapper. All right, and all of this gets transferred to a central location. Now, the first thing that might click you is, why can't we minimize this? Why can't we shrink the data before sending it to the reducer, right? So when you have this kind of data on each mapper, so mapper 1 might look like this. Mapper 1 will spit out A1, A1 again and again, and the data will get sorted on the mapper 1. And similarly, there will be mapper 2, there will be mapper 3, and so on. And this with this all of this data will get transferred to the reducer and will be combined over there, right? So you could do multiple things. You could do multiple things in each mapper. First, you compute the frequency of characters for the whole line and then print out that frequency instead of simply printing A1, A1, B1, C1. Instead of printing out Just like we did word count, instead of doing it that way, we print out the frequency in each line, because each line is available to the mapper, right? To your code, each line will be available. Second thing you could do is, before the data gets sent to the reducer, if we could put a code which basically shrinks the data before, or which basically computes the frequency, which totals all number of occurrences of a on one node before sending out to the reducer, then our half of the headache is gone. So remember and remind me when we talk about something called combiner. Okay, something called combiner in upcoming slides. All right, so this problem is basically solved by using a combiner on each node. Okay, so I hope nobody has a problem up to this. Combiner, when we discuss combiner, we'll talk about this example again. Okay, all right, so moving on. Should I move on or should I explain it further? Yes. So basically all we did was did the computation of frequency in a single line, printed that, and then handed over to that to our mapper. I mean, mapper will print out the whole frequency of characters in a line, and then reducer will combine them. All right. Now, this is important. This is interesting and important. So, anybody has been able to crack this problem? So, did anybody solve this problem? If you have, you have to find anagrams in a huge text. Okay. Could you just brief your approach, because I am not able to locate right now. Excellent, excellent. So I can see Tuntun's answer here in the solution also. Read the data line by line, split. Perfect, perfect, perfect. Okay, okay. So let me look at other answers also. Yes, anagram can have same letter appearing twice. All right. Satyanarayan's answer is, check the length of both the words in string. If they are equal, then only proceed to check for anagram. Else, nothing to do. So Satyanarayan, the problem is to break the problem into MapReduce. Can we use the MapReduce paradigm where we print out keys and Hadoop sorts by keys and then you use that information? Or can you convert the problem of finding anagrams into a sorting problem? If you can convert this problem into sorting problem, then you can do that. Good. Although your approach is quite close, where you say sort both the words and then compare. I've taken a string tokenizer where comma is delimited and kept a string array, sort the array, and iterating each array. If those are equal, if map is like act, the value is like act, cat, tech. Yes, you are right, Prashant. Alright, so the answers are coming at fast rate. So let me just paste it in here and read it. Okay. I have taken the tokenizer as comma, deemed and kept a string array, sort the array, iterating each string. If those are two were equal, sending the string and one to the reducer. Okay, okay. No, actually, let me. For each string, counting the number of ones, printing the output. Okay. No, I didn't get it. I have a token string. I've taken string tokenizer where comma is delimited. You don't need to take a comma. You can simply break down the string by iterating from left to right and kept a string array. Sort the array, iterating each string whose values are equal. Whose those are equal. Okay. Yeah, but that's not. See, in map, you will not be getting, to be very honest, in map, you will only be getting one line at a time. You will not get the whole input at a time. All right. So you have to, build the problem accordingly. Okay. Sort each word and prepare each key value pair as follows. Okay. Good. Good. Sashikant's approach is correct. Perfect. So Tuntun's answer is correct. Sashikant's answer is correct. And Prashant's answer is correct. Rest I have not checked yet. Okay. Good. Purushottam's approach seems correct. But both the strings we cannot right away compare. We have to locate them. Good. Good. All right. Arrange the words in all possible combinations and make the same as key and value would be the input and then forward to reducer. Arrange a word in all possible combinations, okay, and make the same as key and value be input and then forward to the reducer. Okay, okay, that's also a very interesting approach. Okay, that's also a very interesting approach. Now the problem is, so I'm looking at Karthik's approach, which is far different from others. Now here, let's take an example. What he's suggesting. So we have cat, tech, and act, right? Or let's say we have two different lines with this. Okay, art and red is and off. Let's say we have these two different lines. Okay, so what he's suggesting that, or let me just remove, make it very smaller. we are having only this. Okay, so what he's suggesting, take cat and generate first cat cat, then generate act, then generate tac, then so first a, and you could also do this. All right, so you will basically generate these many ones, and everywhere you'll have this. That's what you're saying. And you have off, and fo is also off, right, Karthik? Okay, okay. Okay, so you mean to say that one key for all combination. All right, and what is that key actually? That's what I'm more interested in. Actually, I'm more interested in understanding what will be the key. Key is basically care sort. That is good, right? So that is good. You don't need to do that. Okay. So that is correct. Yeah, I got it right. Actually, I confused your answer with Pawan's answer. Okay, this is correct. This is correct. Yeah. So Pawan's answer is arrange a word in all possible combination, make the same as key. Value will be input and then forward to the reducer. Yeah, but in reducer you will have to do a lot of things. Here, here, if you see in reducer you'll have to do. I'm answering to Pawan. Okay, this is Pawan's approach probably. Yeah, and for this you will have a similar set of things. It's going to be difficult to combine them together. It will be going to difficult to combine them together and bring all of these together. All right. So the approach, the one which others have suggested, I like that approach, in which you basically the characters, sort the characters, and then sort the characters of a word, and they make that as a key and put the value. So all the anagrams will have a same key because all the anagrams are nothing but rearrangement of the same letters. And if you rearrange all the letters in an ordered, so all the anagrams will result in the same sorted string, right? And therefore that key will become common for all the rearrangements. Sounds good. All right, so great. So this class is wonderful. We generally have one or two people out of 20 who can solve these problems, and interestingly nobody actually talks about map reduce beyond word count. Okay, so so great. I'm pretty happy that the class is really working good. Okay, so we have solved the anagrams problem. Perfect. So should I explain it again or should I move on? Uh, Those who want me to explain again, feel free to ask. Sometimes it's not it's that straightforward to get it in once. Should I move on? Okay, perfect. So moving on. Now that was our anagrams, and this is our another problem. So this problem probably everybody has done this. Okay, you haven't reached till there. Okay, okay. I'm just picking questions randomly. Okay, so this is okay. All right. Good, good. So yes. So what is your solution actually? Okay, so you guys have solved it. So one of the solution is that there is a mapper and key is AGCT and value is user1. Okay. So basically the key becomes the DNA and value becomes the user, and that's all. Perfect, perfect, perfect. This is great. This is great. All right. So so anybody has any doubts? The answer is simple. Mapper will spit out. Mapper will simply spit out the value, the DNA as the key, and the user as value. So people with same DNA will come together. Any doubts here in third A? All right. All right. Cool. Now, now third B, third A is clear to everybody. Third B is little difficult. Okay. Third B problem was third problem statement in case of third B is people with the same DNA. Okay. Okay. So uh, your in Tuntun's answer, the question number six, point number six in the mapper. After sorting, make one word using words from sorted list. You mean to say that okay? You mean to say that the key is basically combination of the two words in order. Hmm. Okay, let me think if I can break it. No, you can't break it. Yeah, all right, all right. Good, good. So this is one answer. What Tuntun has given, that is one answer, and this is correct. You could actually do a little better, although not much of a benefit, but still it could be made a little better. So anybody else got the answer? Hmm. So Shasikant, here in reducer, you are trying to assume that you will get a list of all the DNAs and No, that would not work. That would not work. Because the way in your reducer, what you will get is this key and the value as a single input. Okay, all the users with the same key will come to you, but the mirror image will not appear together. Okay, the mirror image will not appear together. Okay, so the question again is, we have to bring those users together whose DNA is either identical or mirror image of each other. Okay, so here you have a list. Now this list, where did you get this list from? That's my question. So for first, imagine this first list will basically contains only user 1 and user 4. Okay, and this is maybe in terabytes. So reducer will get essentially the values for a key. Okay, so anybody else solved it? I'll have a look at it. Okay, okay. So Karthik's answer, I need to understand what does same hash word mirror, what does that do? That function you have put, what does that do? Exactly, I'm looking for the answer of that one. That hash function which you have decided is, I want to understand that one. The approach is perfect. Approach is perfect. Okay. Return same hash key for word and mirror word. You mean to say the hash code of Java or MD5 hash, or you will design your own hash method? So remember, whenever we use a standard hash one, multiple words result in the same hash code. You know that part, right? Multiple words, even though they are not identical, they result in the same hash code. And how would you ensure the combination of word and mirror word is always identical for all the keys? I think this will not work out as ACGT and AGCT is there. Right. So Nasruddin's suggestion is, in reducer, read all the DNA sequences, user in a map, and right. So see here, the whole objective of our Hadoop, our map reduce is defeated because you have read the whole data into a map. Right? If the data is bigger, then the whole it would the approach of reading everything into map is not something possible. right? So actually, your approach is correct. You just need to translate your approach into the key value pair. So the approach which you have used for preparing the key when you are putting in a hash map, you can give the same thing to Hadoop in the form of key value, and Hadoop will do the same thing for you, right? We can divide the input string, take out the DNA from the string, sort the DNA, but that is same as anagram, isn't it, Pratik? If you do that, ACGT and ACGT and AGCT, ACGT and AGCT will both result together, right? As per Pratik's approach, right? Even if you check the length, it's the same thing, right? Right, right. So far, only one solution. I'm pretty happy. At least one is there. Generally, I don't get even one. Okay, okay. Or maybe I'll go through your answers again. All right. I'll go through your answers again and come up with your own approaches. All right. So here is my approach. One approach was by, I think, okay. So Karthik's approach is also quite closer, and you are almost all on the same page. It's just that you need to turn your problem statement into the map reduce. All right. Great, great. So, all right. Thank you guys. So let me go ahead with my solution. Although it is just one solution of multiples. So what would I do is I will do the inverse of DNA, okay, and compare with this one, and whichever is smaller, I will pick that up. Okay. So for this one, for AGCT, for AGCT, the inverse is going to be what? TGCA. And which one is smaller, this one or this one? Good. So this one is smaller. All right. So this become our key. Okay. You could also choose the bigger one, but then in both the cases you will have to choose the bigger one. Okay. If again another key comes, okay, if another key comes, okay, so what we did was we did an inverse, okay, and then we did a comparison between these two and we resulted in this. All right. Now if again ACGT comes, if again ACGT comes, the inverse will be the same, and again the result will be the same, right? But in case, so the key is going to be, okay, ACGT here. In case TGCA comes in, the inverse is going to be ACGT, and the key is going to be this one, right? Because smaller is the one which we are picking as the key, right? So effectively we made sure that the mirror image, the the users having the mirror image of DNA as well as identical DNA come together. Okay. So one of you have given a solution in which you said that you could combine these together in this form or in this form. Okay, so that answer is also correct, and this one is also good enough. All right, so effectively we are making the key such that those values come together, just like in a hash table when we prepare the key, so that when we next time try to put something in, we find the same value. Okay, so objective is to form the key such that the values which we want to bring together, Hadoop will bring those values together for you. Okay, sounds good to you? Move on. Great, great. All right, so you have to basically generate the key in a mapper such that the all the values which you want to bring together should have the same key. Okay, which all values which you want to bring together should have the same key. That's the kind of key you need to generate. In case of when we were checking for anagrams, all we did was sort the characters in a word so that all anagrams are together. In here, where we were checking for mirror image, what we did was we mirrored the word, compared the mirror one and the actual one, and then checked which one is smaller. Because for mirror and the word, if we do take this approach, the key will always be the same, right? Key will always be the same. So, all right. So moving on. So who has attempted this question? Okay. So the first one is mapper, voter, and okay, votee and voter one, voter two, and so on. Good, good. And so we got C and AB together. Okay. Okay. So here the only problem is the voter here. Okay. So voter, you have made it as an object. This is what I understand, right? So voter, you have made it an object, and worth is given over there. All right. So whose answers are these? These are Shashikant. All right. All right. Okay. So your answer is read the list. Voter will be the key and value will be the voter. Votee will be the key and value. Okay. So that all the people who voted for one come together, also include voter will be the key and value will be 0 or empty. Okay, okay. Repeat for all the list. Okay. First we load the list to store all the values in map. Oh, that is the problem. That is the problem. So here the problem with this is store all the values in map, and that is going to be a problem. Distributed cache is the first common fallback we fall upon, but can we do it without, because a distributed cache is not, because if you have a distributed cache and you have copied this data all over, remember this data is for each users, and each user is millions of users. It can go out of memory, yes. All right. So whenever you're joining two data sets which are really, really big, distributed cache is not the way. This is basically what we are trying to do here is we are doing a standard SQL join, right? We are doing a standard SQL join using our MapReduce paradigm. And when we join two things together, we join on a key. So we make that key as our whenever we joining two data set, we are joining on something, and that something becomes our key for the mapper reducer. Okay. So here, when we are joining these two, list one and list two, we are trying to find out first the wealth of the voter, right? So if we make the key as the voter itself, okay, key of the voter itself along with this one. So when we join the list, it is going to get us the wealth also. Okay. So my solution is, has anybody else attempted it? I like to have a look at it. Yes, I'll like to have a look at your solution. You must have done it here, right? Somewhere. Did anybody else attempt it? Not yet. Okay. Okay. Yes. Okay. 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 You are almost there. You're there. Yes. Good. All right. Although I'll get everything checked. Okay. But this is just for taking up the discussion. Okay. So yes. So Prashant, you're quite close and you're on the similar approach. So first approach is that we merge these two lists, keeping the first column as the key. Okay. So we concatenate these two files, list one and list two, and this is what we get. If we concatenate it, we'll get this one, and Hadoop will do the group by for you. So we got A, in which there is a number, and then there are other votees, right? Now there is another map too. What we have done, this is an step which is quite interesting. Okay, once, so first phase, it has two phases effectively. In the first phase, we merge these two lists to generate this one. Okay. So for a mapper, in a mapper, we did nothing. We just said first column is our key. That's all. And we merged these two. The way we said, we just gave a folder. Similarly, we gave a folder to the map and said this is our output. And then we get this one. Once we get this one, we generate our result in this following manner. Each line is saying that the voter A has voted for B and C, and A's worth is 5. Similarly, B has voted for C and B's worth is 1. C C has voted for F and its worth is 11. All right, and so on. That's what it will do. Now, in case of mapper, the second phase of MapReduce, it will get the whole line as input. The whole line will be provided to map second phase of the map, the next mapper, as input. So what it does is it forms, it tells that the key becomes the guy whose worth we are computing. So we are computing b's worth. Now b's worth is 5, right? Because A voted for it. By virtue of this voting, B gained 5, C gained 5, A got nothing. We have put A got nothing because we want A 0 in the output. Okay? We want A at 0 in output. Similarly, that the same thing we did for the second row, third row, and so on. All right? So basically, we made the key as the votee and the value as the vote count due to one individual, right? Due to one voter. And in the reduce phase, all we did was summing the values. So for A, after summation, it's still 0. For B, after summation, it's 5. For C, after summation, 5 plus 1 plus 0, it's 6. And for D, it's 0. And for F, it's 11. Okay? So is this approach clear to everybody? The important aspect is this step where we just joined the two tables together and formed the values in this form. Okay, sounds good to you? No? So basically this is how you do. Okay, so basically what map 2 does is pick up the first value. Value is an array here. Value is an array. Out of that array, zeroth number is the value for rest of the elements. Why? Because the if you look at this line, it basically says, if you see the significance of this number, it says that A voted to B and C, and A's worth is 5, right? And therefore, by virtue of this line, what is the value? What is the vote count? B got 5, C got 5, right? Similarly, by virtue of the second line, C got 1. By virtue of the third line, F got 11, right? And therefore, value of now in the next phase, what we want to do is value of B, because of all the voters we want to count. Therefore, the B becomes the key. Similarly, C becomes the key. The meaning the people who got voted by others becomes the key, and value becomes the voter count, voters' wealth. Sounds good? No? Yes? Okay. Should I repeat or is it clear? Perfect, perfect. Great. So if this is clear to you, if this is clear to you, yeah, yeah, go ahead, Sasikant. Sorry. So yeah, so Gayatri's question is very good. Gayatri says that will we get will we get BC5 is possible, right? Yes, it is definitely possible. But in those cases, if you concatenate in the order like list 2 and list 1, the sorting which happens in case of mapper by Hadoop is stable sorting, which means if there are two values, one is smaller than the other, A and B are both same. In those manner, they will come together and the order will remain as is. Okay. Or the other way what you could do is you could, in case Hadoop was misbehaving, although this is Hadoop does stable sorting. In case, say in future Hadoop stops doing stable sorting, what will you do is you just do a pass and figure out which one is numeric and then print it out. Okay, consider that as All right, let me answer. So Gayatri, your doubt is clear, right? Because you are saying BC5 is possible, right? Sorting based on key. Yeah. All right. Are you doing this with one mapper? Yes, I'm doing this with one mapper. All I did was concatenated two files. The way when I was demonstrating you the streaming job in which I provided the full folder. Okay. Similarly, I'll do that for you in this one also. So both the files I provide as input to my mapper, and I get a concatenation of both the things, and then my mapper does nothing, and we get a reducer. Okay. Interesting thing would be to actually do it on our cluster. Okay. Now, Purushottam's question is, can we explain after map 2? Okay. So after map 2, all we did was we noted down, we 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 picked up each voters. Okay, each votees. Basically, these are votees, not voters. Voter is A. Okay, so we picked up each voters and just printed out one 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 line at a time for each votees. Okay, and the value they gained because A voted for them is 5. Therefore, B got 5. B is the key value is 5. C is the key value is 5. A is the key value is 0. You can ignore this part for time being. This I'm doing so that even if nobody votes for A, still A is in the output but with the 0 value. That's the only reason I'm doing it. Okay. Similar is the case with C. All right. And so on. Purushottam, sounds good? All right, all right. So all of you, if you got this correct, all of you are ready to actually convert any problem into MapReduce. Okay. If you got this one, okay, and the previous one also, you should be able to convert any problem into MapReduce. And this effort of being able to convert most of the problems into SQL does not go waste, even if new paradigms such as Spark come in, because they also, all of those work on the MapReduce paradigm. All right, great, great. So moving on, let's take a break of 10 minutes, and then we go with a Java MapReduce. All right. Hi guys, I'm back. So are you guys back? Alright, should we start? Great. So yep. Should we start now? Alright, so only two guys. So only two people are saying that we should start. Let me wait for others. Alright, so yep, let's start now. Great. So we just proved that there are a lot of problems that could be solved using MapReduce paradigm. We took those for example. There are few cases where you should not be using MapReduce. For example, if the job can be fairly achieved using a single machine in reasonable time, there is no point in doing it on the cluster. Other than testing and learning, there is no point of doing something which can be fairly achieved on the local node or a single node need not to be done using Hadoop, because the amount of time that goes in transferring data across the cluster and doing a lot of things might take a lot of time, and you may not be happy with that overall performance, and then you may say that uh, Hadoop is not great, it doesn't solve my problem, it's quite slow, a single machine is better than the Hadoop, right? And in fact, that is the fact. So in case your single machine is faster than Hadoop, there's no reason to do use Hadoop. Okay. Now, next one is when the computation depends on previously computed value. For example, if you are doing a recursion, or if your problem statement requires solving something like a Fibonacci series, and remind me what exactly is Fibonacci series? Do you guys remember? Just first answer. So previous two numbers sum is the Fibonacci series, which means which means which means that computation of third number requires first two numbers, and computation of fourth number depends on second and third. S- so such scenarios where you need to depend on when computation of ith number depends on any other I minus 1, you cannot distribute such kind of problem onto multiple computers, and therefore it does not make sense to use such kind of use Hadoop for this kind of scenarios. And in case you got to do indexing, Hadoop may not be a great solution. Okay. There are other solutions available for indexing or ad hoc searching. Now, second is whenever your algorithm heavily depends on a shared global state. If if on every mapper or reducer you got to look up in some shared cache, whether it's distributed cache or a central, uh, basically a centrally located cache. Distributed cache is still okay, but if your mapper or reducer depends on a centrally located data, which means that for each of the keys, and these keys might go into millions, you might have to do a network lookup, and therefore it does not make sense to have such kind of problem solved using Hadoop, right? But you should note a few things, that sometimes what happens is that because of our inability to convert the problem into proper map reduce, we end up doing a lookup centrally. Say for example, the last problem which we discussed, we could have basically looked up into a central cache, right? So we could have taken the wealth as a central data, and every time we iterate through a value, we start looking up into in the central cache. And that's a common problem. That's a common problem which occurs. Even the senior members who have been doing MapReduce for quite some time, they by mistake end up either doing these kind of things locally, or they end up doing a lot of lookups. Okay, so be aware of this part. So these are the cases when you should not be using Hadoop, you should be using other solutions for such kind of scenarios. Now, how do you test? First, testing MapReduce has multiple steps. First, you test it on small data. Second, you test your mapper and reducer separately. So these are the cases, four cases when you would not use MapReduce. Okay. First, if it can be done on a single machine, nothing like it, don't use MapReduce. If your computation depends on previously computed values, such as Fibonacci series, don't use MapReduce at all. Third, full text searching or ad hoc searching. Okay, because when you search, you need to quickly look up things, and Hadoop is a batch wise process. So you cannot start routing your search query to MapReduce and then make your user wait, right? Fourth is when your algorithm depends on a global state. Okay, when each of mapper or reducer depends on a global state. In those cases, each line, as you we studied earlier, for each key value, you will end up making a central lookup. Right? Is this clear, Lavanya? All right. Now, testing is important. Yeah. So, examples, as I told you, if as we talked about, if the data is smaller, say for example, if your data in the size of say 50 MB, and you can fairly easily load it on a single machine, then you don't need it. Okay, that is first example. Second one, Fibonacci series kind of cases, or in the practical world, what could I give you a good example of the second point? Second point answer would be that, okay, this requires a bit of thinking. Hmm. Okay, so let me give it a thought. If I can come up with a practical example instead of a Fibonacci series, I'm not able to come up right now, but okay. The third one is fairly straightforward. You should not be doing something on Hadoop for which your user needs the answer right away. If your user wants a certain output right away, you should not be doing MapReduce for that. Okay. Why? Because because MapReduce has got a high latency, and for the high latency kind of thing, the task might go up to 10 seconds, 15 seconds, or there may not be any answer at all. There might be some error on your cluster, right? So in those cases, it's not great. Top 10 records based on their transaction map reduce, because after reducer completes we'll be able to do top 10. Right. Right. Yeah, it was breaking for a minute. All right. Now Prashant's suggestion is that top 10 records based on their transactions MapReduce is not suitable because after reducer completes, we'll be able to do top 10. Right. Right. So, yeah. So there are many such problems when you can realize that they can be fairly done either on single machine or the computation depends on previously computed values. Okay. So, I mean, the second one, I'm not able to come up with a good example right away. One case would be there is a tree structure where you have to compute from bottom up. In those cases, you have to do the computation from bottom up. Is it still breaking too much? Not clear. And now, is it audible now? Oh, okay. Doesn't look like a problem. D- Wait, wait. So, hello? Just a second. Just a second. Yeah. Can you hear me now? Great. Great. All right. So moving on to the next step, the testing part. All right. So when you test any mapper reducer, these are general guidelines. When you are testing your code of mapper reducer, first you should be testing it on a very small data. Okay. These are, although these are quite a common sense, I should not be even telling you, but generally we forget. Okay. So no matter what is the data size, mapper reducer always result in the correct output. Okay. Now, second is the only problem we will see between the small data and big data is we might be making a mistake in doing the computation such that we might be consuming too much of RAM, too much of memory on each node. Okay, that can only be done when you do a testing on big data. Okay, but before that you can be fairly happy with the small data. I have faced a scenario where we tested on a small data forever And when we were doing it in the production, we realized that we were consuming too much of memory. And that was a mistake on our part because we ended up doing a lot of things locally, which was completely wrong. Okay. Which could be easily done using Hadoop itself. So that is one thing. So basically, you can have a look at one of my blogs where I have written a problem about a recommender engine. So that's where we basically ended up testing only on small data. We did not test on big data. Okay. So first test on small data and then test on the real data. Second is separately, which also tells you that you should have a Hadoop cluster. Whenever you have a production environment of Hadoop, you should have a small cluster of Hadoop for yourself for testing. Second, separately test mapper and reducer. Okay, separately test mapper and reducer. That makes your problem statement smaller. Okay, so if you write test cases for mapper separately as well as reducer separately, so you will be able to clearly tell in later point of time that which code is breaking. Okay, though none of us does it, but when it comes to production environment and doing really good thing, you should always be testing your mapper and reducer independently. Okay, then if there is a streaming job, if you have got a streaming job, you should be using, you can actually use this Unix command to test your output very quickly. Okay, this is an equivalent of a streaming job on a single machine local. Okay, if you have got Java map reduce, you will use MR unit. We'll show you. Fifth is to test predictions. So lot of data when you deal with in big data and Hadoop domain, you basically will see that the jobs you are writing, most of the time they are for prediction. Okay, and when you are predicting anything, the best way to test predictions is divide the input data into two halves. Use the first half as the input while the second half for asserting the data, and the way you divide this data is using the timestamp. Okay, so it's like you are given a 1 million ratings of movies. Okay, you're given 1 million ratings of movies, so you divide that data into two halves. Okay, by timestamp. Now based on first half, you generate the recommendation for the users, and second half you consider as the fact. Okay, so it's like if there is a guy who is telling the future, you are asking about the past. Okay, and comparing it with the past. Only then you validate that this guy is telling a truth. Similarly, when you are building predictions, you try to uh, predict the past and compare it with the past and then move on. All right, that's how most of the prediction systems are built. Now, next part of the session is about MapReduce in Java. Okay, so when you do MapReduce in Java, you basically pick up basically, first of all, you write a mapper, you write a reducer, and then you write a driver, which starts the mapper reducer process by stitching mapper and reducer together. All right, so this is what it is. Now let me show you in Eclipse step by step. All right. So here is, let me just close these projects. So, so how many of you are comfortable with Java? Okay. Okay. Wow. So almost all of you are comfortable. Great, great. All right. So step mapper. So you can download an example of MapReduce from the MapReduce project from the course and import that project into your Eclipse. Here the steps actually. All right. All right. This is a question we will discuss tomorrow. One, two. All right. Now, all right. Now I'm going to demonstrate to you how to write in Java. First is, why do you need to write it in Java? Because first, it is good for those who know Java. Second, primary support of Hadoop is for Java, and you can modify the behavior of MapReduce to a very large extent using Java. All right. Now here, so first of all, install Eclipse. You already have that, and then create a Java project. Okay, create a fresh Java project, and then add all the libraries. Ideally, only these are sufficient, but the libraries are available as part of in my courses. If you go into the session number 4, in the session number 4, not this one, not this one, not this one. All right, here in the session number 4, there is a sample project. You can download that project, and in that there is library available. Okay, so when, and then you create a class. Also remember to change this to 6 from 7, because there are some systems, which some of the Hadoop clusters which still have the compatibility with 6. Although this is a decision which you need to take in conjunction with your cluster engineers. Okay, that which Java is installed on the cluster. Okay, so if you have compiled your MapReduce in 7 and the JDK which is installed on the cluster is of the version below 7, your MapReduce will not work. But if cluster has Java 7 and you have compiled in 6, it will work. Okay, so that is why it does make sense to do it 6. All right, and it in whether it is installed or not, you can always change it to 6. You can say Java build, Java compiler, and here you can say compliance level as 1.6. All right, you can say enable project specific settings and change it to 1.6. All right, it's just a safety step. Now once you have done that, and also here the there will be a library also. Here we call builder, not builder, Java build path. Here the library, you can have add library and put Java. Okay, here you can basically, it will show you all the options. If you have Java 7, it will show you the Java 6 option also. All right. Check with your cluster, and even if you made a mistake right now and it worked on locally, tomorrow you will have to just recompile, and that's all. Okay, so the first step in the process is writing a stub mapper. Okay, stub mapper, basically it's any class name. You can write your own class name here, whatever you feel like. Okay, and they all need to extend something called mapper. All right, by default, by default, by default, you will be the and you will be defining, when you are defining a mapper, you will be telling that what kind of mapper do you want. Okay, what will be the keys and values. So key here is an object which is a byte offset, which is provided to you by the file system. Okay, HDFS will be providing you byte offset as the key for the mapper, because when we talked about in, you are getting line as an input. Okay, that is the second argument. The first argument you get from the system is byte count. Which line, this line is start at which byte count. Okay, not the line number but byte count. Now now the these two other key value pairs, this is what mapper will be giving out. Mapper will be giving out key as the text, value as the long writable. Okay, so basically, first, Hadoop has come up with its own data types. Okay, data types such as text, long writable. Instead of saying long, it is long writable. And text, instead of saying string, it is text. Similarly, instead of int, it is int writable. This is done to make the serialization of object really robust. The serialization of object which was there in Java was not was not suitable for a network kind of a model. Therefore, they actually created few more classes to represent the primitive types. All right. Now, this is what you need to describe. Okay, in the first, and after that, your definition of map, you will have to override a function called map, and the the same data type will be here. Whatever you have defined here, if you have defined object and text, similarly object as key and text as a value will be provided to the map, and you will have something called context, right? Now the input line which we have always talked about will be the second argument of this function, which is value here. And what we are doing here is value dot to string, and split this string by tab or spaces, right? And once you got these strings, we print out into the output, which is context. Okay, so in context, we keep on writing the output of the map. Okay, context dot write, and since key is going to be a string, therefore we created a new class called new text and gave the word, and then we said new long writable, and then put one instead of blank. All right, so it is equivalent to saying our output of mapper is key comma 1, key comma 1, key 1 comma 1, key 2 comma 1, and so on. Okay, and the key is here, each word is the key. Each word how we have generated, after breaking the line, after splitting the line by space and tab. We splitted the line by space and tab, we got an array, and then we iterated over array and printed to the output, output as in into the context, the key and the value. And as I told you, the string as represented in Hadoop is in the form of a class called text. All right. And long, because why we are using long? Because the data might grow big. A word might occur a million times. All right. So this is our mapper, or a billion times. The int, normal int, may not support that much. All right. So this is the definition. This is how you create a mapper, and this is how you create a reducer. All right. This is how you create a reducer. Sounds good to you? Now, in case of reducer, you extend, this is your class name. You can write any class name. My reducer class, or whatever you want to write. This is yours. And you create, this is one class, this is another class. And once you have done that,
Hello.
okay, I think the connection is stored. Connection seems to be flaky somewhere. All right. So when we are talking about reducer, in the same paradigm as mapper, we create our class that extends a reducer. We define what is input and output, and context is the object via which Hadoop gathers the output from reduce as well as from map. Okay? Mapper as well as reducer give their output to the context. Okay? And there are many other variables which are available as part of context. You will see very soon. There will be other variables also which are available as part of context. Okay? Now, now you can look at the mapper, then you have reducer. Okay? So we write the key into context. Okay? We write the key value into the context. No, I did not get Sasikant. So we are not writing into the file, we are writing into the context. Okay, context is an object given to you by Hadoop. We'll keep on putting it. We can do, yes. We could also write something like int mapper, int writable, and we could write it without any issue. The only thing is you will have to say int writable as the output over here. Okay. Each split has separate context. So no. So each input split has a separate context. I mean, there are many variables in context. If you see, okay, it gives you access to the arguments given at Hadoop command lines. It gives you access to the configuration. It gives you the access to many other information. It gives you the details about the job ID. Okay, and the context is basically a single link across the whole jobs. But right now, you can think of context as someone who gathers your output from all of all of maps and reduces. So context will be common across all the reduces as well as across all the maps on the same machine. Okay, but it won't give you the data from other reduces. All right. Now each split has separate context. Yeah, context. The context of the mapper here, both mapper as well reducers will be doing some sort of magic inside it. Generally, the mapper, when you are outputting from a mapper into the context, it is going to put in a circular list, and then will be doing all sorts of partitioning here itself, and then spilling over to the disk. Okay, so context effectively stores all the output from both of these. It manages everything very well, right? So this was an example of people. If you want to debug in production environment, you can write to error or sysout, and then you can debug in the logs. So three mappers, it most likely will be a different context objects. Okay, and you will not have access to one another. Once the context object is created, yeah, see context object, if you see, if you look at the you know look at what does context look like to you, not this one. Context look like, so it gives you various configuration parameters. It basically gives you all the information required. Okay, so most likely a context is same across all, but it does not mean if you change something here it reflects over there. Okay, it's a copy of the central object. Okay, when you make a write here, when you write over here, it's equivalent to saying system.out. Okay, although system.out is same across all the Java programs, but that does not mean you can access system.out in other machines. So yeah, so yes, mapper reducer will have different context, of course. You cannot communicate from mapper directly to reducer via context. So you can have a look. Although the class definition is same, you will have lot of values available here, right? But these are though though it's a copy of the same object, you may not be able to communicate with mapper to reducer via this object. All right. So context is an object where you keep on outputting your input, or if you want to read some config file, you get it from context. Okay. Context provides you the output stream. See, how should I describe this? Okay, so see, context in the sense is same that it gives you the common configuration. You get the common configuration from all of the objects. But as an object, okay, it does not make sense to say that mapper and reducer has the same context. Why? Because reducer might be on some completely different machine, while here on one machine there is a context. So context is sort of uh, available across the you know on the same virtual machine, having some values, but but this context is always, how should I describe this? So let me explain it again. Yep. So this context is basically a copy of a centrally same object, in which you keep on writing. When you write to context, you are not changing the object, you are writing to a stream. Okay, so context is fairly sort of a mutable object. Okay. The only thing you can change in the context is the status. Okay. So for each task, you got a context. For each task, you got a context, and Under each task, there could be either reduce or map, either of the two. Okay, and then you can write the data to it. All right. So let me again repeat myself. The whole process of Hadoop is made up of two kinds of things. One is mapper and reduce. For each mapper, there would be tasks. Each task get executed on a one machine. Each task has got an attempt. We make an attempt in a task. And for each attempt of the task, we have got a common context, right? And in each of this task, there will be multiple times. Your stub mapper will be instantiated only once, and your stub mapper dot map method will be called multiple times for each record. Okay. Similarly, for each reducer task, stub reducer will be created once, and stub reducer dot reduce will be called on each key which is given here. And for all of these, the context is going to be same. Okay. So context is one per task. Sounds good? All right. The only thing you can communicate out is by writing to context, which goes as key value pairs. And the other way to communicate is by setting a status. If you get an error inside reduce, you can set the status. It is one per task. A job comprises of multiple map reduce tasks, mappers as well as a job comprises of either multiple mappers or multiple reducers. So this is one per task. The whole thing is a job. When we submit it, its whole thing is a job. All right. Now, so that's how we write a reducer. The next step is to create a driver. Create a driver over here. So how do you create a driver? Driver is the one which is going to be your entry point. A task means either mapper or reducer. Suppose a job is divided into 10 input splits. A job is divided into maps and reduces. Inside map there are 10 input splits. Okay. So each job has got multiple tasks. Task 1 is running on one node, task 2 is running on second node. Each task has got some input splits. It could be 10, it could be 20. Right? So let me again reiterate. So you got a job that is divided into 10 input splits. These 10 input splits means 10 is mapper, correct? And each 10 input splits will create 10 context object, and one reducer will be there, so there will be one more context object, which means 11 one. Right. All right. Now let's go ahead, but that is immaterial generally. The context object is fairly stable concept, so you don't have to worry about creating number of context, because that is something created by Hadoop and you don't have to worry about that part. Okay, what we need to worry about is how do we stitch stub, mapper and reducer. So first of all, you create something called job config. On top of job config, you create a job, and then you set the driver. Okay. So here you say that this is my entry point. Whenever you are creating a jar and you want to define an entry point, then you can define it like this. Okay. So step driver, out of step driver's class, out of whole bundle, step driver is my entry point. Okay, that's what I have told to the job. Now we define that this is my mapper, this is my reducer, and rest of the things are optional for time being. Okay, and here I am saying that add my job as add input path as well as output paths from arguments. Okay, and also I have defined in case user does not provide uh, arguments more than equal to 2, then it gives an error saying this is the input path. Now are you able to see my Eclipse window? Eclipse. All right, now, all right. Yep. So here you keep on defining, then you define number of reduce. You remember we discussed this now, how many number of reduce you want. In case you want 10, you can say 10. Even if you have 4 nodes, still you can say 10. All right, and once you're done with it, you can do an export. Okay, partitioner we will discuss, don't worry. Partitioner, combiner, we will all discuss all of this. Right now you can actually comment out partitioner. Now I'm leaving for reduce tasks. Okay, or let me just keep it to, all right, and there we go. Okay, so here there is no necessity because the kind of data I'm going to churn has got a small reducer. Okay, reducer will be quite quick, right? But just for the example sake, I am doing a set number of reducer to 2. All right, now let me export it. Okay, so in driver class, what is the need of set jar by class, right? What does it mean? We are telling the job, where we are telling Hadoop that this is our entry point. So whenever we say Hadoop jar, this is where it's going to look up and find how to initialize it. So if we comment out the partitioner, still there will be no difference. All right, I'll tell you why. That's just an optimization step. Okay, so once you have sorry. Okay, now, so what will we do is first we'll do SCP in case. So the next step is export the jar, SCP jar, to our Hadoop server. Okay, this needs to be copied to the Hadoop server. So here I exported the data to SCP downloads, and then say word count dot jar, and I say student dot at Hadoop one dot nobigdata.com, and there we say colon as Giri, which means it will go into that folder. All right. So this is what I'm copying from my local machine, which is my Macintosh laptop, from the laptop to Hadoop one.nobigdata. Okay, I've copied it from my laptop to Hadoop 1.no big data. Now it should be available in my Hadoop one. Okay, so this is my Hadoop one. Now if we see ls, so we should see a word count example here already, and let's see what is ls minus l. So it has been modified just now. Okay, now if you see, so it's showing in est, not local, because it is located in us. And after that, you have got, next step is to do run using following command. Okay, all right, let me correct the command because we have changed the file name. So whatever jar we have just copied, okay, also note that which something you important, the jar which we are executing does not need to be in hdfs. Okay, it need to be locally available. So our word count dot jar and step driver is our entry point. Okay, this is where our entry point is. So we are telling Hadoop to consider this as our entry point, and then this is our input file, argument 1, argument 0. This is what we have coded in our program: argument 0, argument 1, input path, output path. This is what we have coded in them. Okay, let's just try not giving these things and then see what does it say. So which means our program is running, right? Because this is something our program is printing, this one. Okay, so there's nothing wrong with the program. Now we can specify our input folder, which is users student word count input, and then we can say users student skiri slash word count. I forgot where did we keep our file. This file is located in user slash. Okay, so either we can provide it as a full path like this, or we can say it this way. Okay, and we can also say user, not users, user student as Giri Java out. Right, so let's just run the job. So it is starting the job, and as with any task, you will see the URL to track is here. Okay, so you can open that in your browser and start checking what is there. Also note that we had put in, just for the demonstration sake, we had put in our error log. Okay, we'll show you where did this error log go. Okay, also note this one. So this is my error log, which is I'm printing in mapper, this I'm printing in reducer. So let's have a look at it. Okay, so it says stub mapper is not found. Okay, that means we have made some mistake. Maybe in our Java file it was not. It should be there. It should be there. Other than stub driver. So let me refresh it and do project clean and build it again, and then we do an export and jar. So we add everything and say word count. So all of the failed map tasks are 23, killed map tasks are these many, so nothing has actually worked. Okay, it says mapper not found, mapper not found, which is wrong. Why? Because this is absolutely okay. Now, first of all, let's just copy it again. So in case you don't have SCP and you're using Windows, you can use a program called WinSCP. Okay, you can use WinSCP. Yeah, this is the one. Okay, so it says the output folder already exists. Let's see what happens now. So we basically recompiled everything after cleaning the project because it was not probably generating a lot of output. So as you can see that it is there are 14 total maps, 6 are pending, 8 are running. It has broken the whole thing into 14 maps. And so let it finish, then we can see 6 are running. Again, it has failed. Is MobileXterm is good. The, I haven't used it, so I haven't used Windows for quite a while, so I may not be able to tell you. Why does it say stub mapper not found? Right, so ideally it should just work. Am I using a wrong class or something? No, nothing actually. All the drivers, everything are available in this reference libraries. You can see those, and therefore it is fairly straightforward. Such errors never occur. So I think I'm doing a mistake where the old file is being picked up. Let me just make a change and put one. Okay, export generated class here. Let me see. Oh, okay. So, oh, I got it. I got it. I think we need to tell this. All right. Let's just hope that this time it works. That's okay. That error is okay. No job jar. Oh, okay. So it says that no job jar file set. Okay. Did we make a mistake? Oh, I think it has to do something with the mapper. Okay. Hmm. I think what we need to do is here we need to say sg dot stub driver, because there are two stub drivers. One is sg dot count, other is the other one. So I think this time it should work. Yeah, you're right. The deletion of temporary file is useful. That gets deleted anyway. What kind of error is this now? I think this seems to be okay. Right. Let me just try once more, and if it doesn't work, we'll do it tomorrow. So I'm just renaming it to 3 just to make sure that. So this is one terminal from where I'm copying from the laptop to Hadoop one, and this is another one which is on Hadoop one, and I'm running it from here. So let me just keep a copy of the URL to track. Yeah. All right. So this attempt failed, and the error was. Hmm. Now it's just a memory problem, nothing else. So on Hadoop 2, we have memory problem. Hmm. So let me see why are we getting the memory problems on all of the nodes suddenly? Is some process running more, or do we need to add more nodes? All right. So till then, all right. All right. Then let's discuss it tomorrow. Till then, I should be able to figure out, because now we are not getting that class not found error. It's just a memory problem which we were facing earlier also. All right. So yeah. So the same problem which we were facing during streaming, we're facing now also. And yeah, that's pretty much it. We'll see you tomorrow, and we'll take it further from there. All right. Thank you. Have a good day. Bye bye.